In this video I'm going to illustrate a toolbar button that calculates spectra from regions. This means that I'm going to extract from a spectrum a portion of that spectrum that is of interest to me rather than having to use the whole spectrum itself in the analysis. And the reason that I wish to do this is because I'm interested in the background as well as photoemission peaks. So I have narrow scan spectra. These all provide information about the chemistry of the sample, but when I want to understand the relationship between these different materials and layers within the sample, then the background can be very useful. Now, it may not be fully quantitative, but as a qualitative test to understand the nature of the sample, considering the background is not a bad way to go. Now, the problem I have is that I would like to use the survey measurements because these are the only data for which I have background as well as photoemission peaks. And although when I do a PCA on these data it throws up a set of abstract factors, these are too numerous and probably more involved than I actually need to consider in terms of understanding the sample. So what I propose to do is to extract from these survey measurements a portion of the spectrum that produces less variation. So let's have a look at the survey measurement and bring up the quantification parameters dialog window, because the button acts on the regions that I create on these data. So if I create a region and adjust the limits so that it spans the part of the spectrum that I'm interested in, and the reason I'm interested in the spectra up here is because I've got photoemission peaks from vanadium, there's oxygen, there'll be some carbon up here, very small though, but the predominant photoemission peaks are from the oxide and maybe some substrate. But I can be certain that when I'm looking at the spectra over a wider range, I'm seeing inelastic signal from the substrate. So this gives me insight into the depth information within this sample if I can consider a spectrum over not just the photoemission peaks but also the background. Having created that region, I need to propagate to all the other spectra, and then I'm going to overlay the spectra in the active tile. So now each of these survey measurements include a region. I might as well adjust this to refer to what I'm interested in: peaks and background. And other than the fact that I'm going to extract the intensities over this region and make use of the name that I've applied to the regions, which I ought to propagate again, this is the only information that I need to use the toolbar button. So when I say spectra from regions, I will produce a new file that now contains just the spectra and the background region that I'd like to include in my calculations. Now that I have the data that's just focused on the interval that I'm interested in, I can try the PCA again, and let's have a look at what happens now. Before, when I applied PCA to the full survey measurement, I ended up with 4 abstract factors that had shapes that might be related to the signal, and now I have 3. This one looks very much like noise, and I've got 2 that are much more dominant than the third. So I have some hope that I can work out from these data 2 spectra that will represent most of the variation in this data set as a whole. So let's go back to the data in a form that we can work on and produce noise reduce spectra by using only 3 abstract factors to reproduce the data. So those first 3 abstract factors were the ones that I've included when I calculate these spectra. Now that would suggest I'm hunting for 3 different shapes, but I'm going to start off by just attempting to calculate 2 shapes that are able to represent most of the variation in the data. And I can do this when I overlay the spectra in the active tile using the difference spectrum button, and that will allow me to make some adjustments to the data by subtracting one of the spectra from the other, and the 2 spectra that were selected was the first and the last in the list that was displayed in the active tile. That is true when you use the difference button on the toolbar. That's not true if you use the difference button on the dialog window, the calculated dialog window, but on the toolbar it allows a range to be displayed in the active tile, and it will pick the first and the last as that range to perform the difference calculation. So I've just moved down the list, not too far, but I've gone down the list, so I've subtracted a bit of the end of that sequence from the first in that sequence, and I'll accept that as my first component spectra that I will use in a least squares analysis of these data. So let's carry on down the list, and you can see that the consequence of subtracting more and more of the second or the end spectrum in that list from the first in the list is that we are producing a shape that looks much more like a reduced form of the material. This is vanadium. It's a vanadium foil with adventitious material and native oxide. So it's not surprising that we find something that is in a reduced form, as beneath the surface is the metallic form of vanadium. But I need to carry on going because it's not quite fully reduced. We haven't got through to the metal. What we've got is something here which might be a combination of an oxide, it must be because this is the oxygen 2s, and this is the vanadium, and there may still be some metal in there. I can't fully remove it with this data set, but this represents a new possible basis spectrum that I can use in a least squares calculation. So let us now save that one. So we've got 2 spectra, and this is highlighting exactly what I was looking for. My assumption is that the removal of the carbon, which can be seen from the carbon 1s spectra in this data set, has the influence on the spectra at the upper end of the kinetic energy range, lower binding energy range, that the background lifts considerably when we have carbon, and when we remove the carbon and whatever influences are taking place on the oxide and the metal below, then that manifests as this second shape. And you can see that the intensity of these photoemission peaks relative to the lift in the background is very different. So one is characteristic of a material that has a buried layer that is generating background signal to inelastic scattering, and the second one suggests that it is a layer that is closer to the surface, and the inelastic scattering is only due to electrons passing through the material that is being represented by these photoemission peaks. So these are vanadium photoemission peaks, and they are being influenced by a carbon overlayer. So the inelastic scattering here is characteristic of vanadium scattered by carbon, and the shape we see here is more characteristic of vanadium oxide being scattered by vanadium oxide. I'm now going to turn my attention to a different file. This is a second experiment from the same sample. Previous one was a vanadium foil that was sputtered using helium ions of 1 keV. The second experiment is the foil sputtered with argon ions of 200 eV. And the difference between these two measurements is that in the case of the argon ions, we are able to remove enough of the material at the surface that we can see signal that represents vanadium and a bit of oxygen, but mostly vanadium in a metallic form. So there's a combination of some oxide and metallic vanadium. So let's perform the analysis as we previously performed on the helium example that involves the survey measurements, and I would like to pick out the same interval in terms of energy in these data as I used in the helium. So I've got these selected. I'm using the Control tab to move to the window that displays the survey measurement from the helium experiment, and I've got a region set up as we see here. I will now propagate the region from the active tile that we see in the helium file to all of these survey measurements from the argon. So I have now performed that, and overlaying in the active tile, which we already have, that shows that we've got all of the same regions set up on all of the survey measurements from this second experiment. I'll rename the region to be argon. I'll propagate the names. So these all now have the same name with the AR prefix, and so we can perform the same operation, namely create spectra from regions. So I press the toolbar button and we end up with a file that is similar in the sense that it's the same interval, but we now have the spectra from this second experiment, which highlights a signal that we can attribute to metallic vanadium. Now if we do PCA on these data and look at these data, we can see that we actually get signal in at least the first 3, maybe 4 of the abstract factors, and that's because much more is going on as we sputter with argon. So let's return these to their initial state, and then instead of doing PCA on the entire data set, what I will do is select a subset of the data set. And the idea is that we would like to construct a spectrum that does not involve any oxygen. This here is the oxygen 2s. If we remove that from the spectrum, then that will be an approximation to the spectrum that would be pure metallic vanadium. So let's do PCA again, have a look at the abstract factors, and I've made a selection that does suggest we only have 2 abstract factors, so that ought to give us an opportunity of extracting from these data a spectrum that will be representative of metal. So let's return these to their state where we can process the different spectra based on this set of data. So let's reconstruct using two abstract factors and then construct different spectra. Now the first one represents oxide. You can see that this has got oxygen in it, much more oxygen than the last one in this list. So I'm going to the end of the list and we still see a bit of oxygen. So when I go up this list, subtracting the oxide, we ought to be able to remove the peak that we see here. And I'm going to go up and down until I see what is effectively a background. So that now represents an approximation to the metallic vanadium signal. So let's take a copy of the metallic vanadium, and then what we'll do is we'll create a new window. We will go to the experiment, the difference file from the helium experiment, so I can collect now all three of these VAMAS blocks that represent the initial surface, the surface after the carbon has been mostly removed, and the surface after most of the carbon and the oxygen has been removed. So there's still some processing to be done on these data. For example, I see a bit of metallic signal here, even in the example of what ought to be at the surface. So I can subtract, using the difference approach, the metallic peak. So I could argue about which one I choose, but I'm going to choose this one as being an example of what's at the surface once I get rid of the metallic substrate signal. Copy that, and let's move the VAMAS block I've calculated here into the file representing the component spectra. So that represents the combination of these two VAMAS blocks have produced this third one here. So now I need to do the same operation based on the second oxide. It's not so obvious there's metal here, but if there's metal in the first one, there might be metal here in the second one. So let's do a difference calculation and see what happens when we remove metal signal. And I'm watching this part of the spectrum, and I can see that it is changing, and when I go too far, I can see it has gone too far in terms of removing metal from the sample. So let's up until we get a shape that looks plausible for an oxide. So let us copy to the working file yet another example. So this is the first one, this is the first one removing the metal, this is the second one, this is the second one where I've removed some of the metal, and so I now have here three VAMAS blocks containing spectra that are component spectra representing the material of interest to me. So let's align these in terms of a column and give them a name perhaps that makes more sense. Spectra. And the real test of whether I've done this calculation correctly is to go back to my region spectra from the helium, for example, take all the helium spectra and the component spectra through to a new file and perform a least squares calculation. I've overlaid the component spectra in the active tile, I've selected the column representing the data, and using the LA button I can calculate a least squares solution which shows how those three spectra fit these data. And what we see is that the metal peak remains relatively small within the entire profile based on helium. There is some increase at the end. That's not surprising. If you remove a layer of carbon, you would expect to see more of the underlayer, so there's some sort of consistency in this analysis. Let's do one further analysis of taking these through to a new file that contains the regions that represent the argon sputtered material. And so here we have the argon spectra, these are the component spectra, and select, and a least squares analysis produces another example of a fit. And we again, despite having two spectra that are mostly calculated from the helium, we're getting the same sort of result. We're getting a good fit across the background and the photoemission peaks, and as we go through you can see that it is accommodating the fact that in the case of argon we are removing enough material to see an increase in the metal signal, while the rest of the shape is being represented by these two shapes that were calculated from the helium. So there's a consistency in the measurement. It's worth looking at these component peaks in detail. So we've got two that represent signal that you might think is consistent with a bulk material. One is metal and the other is an oxide, and the reason I say that is because the background declines away from the photoemission peaks in both cases. Perhaps less so in this case, but certainly in this particular case of the metal we have a very characteristic shape for a bulk metal vanadium signal. The oxide, on the other hand, this may represent oxide in terms of the proportion of photoemission signal between vanadium and the oxygen, but the background, it's possible that this is including some component of signal that would have arrived in the background as a result of a substrate that is metal. And similarly, this final form of the spectrum, which is again vanadium oxide, the background itself will be a result of vanadium from the chemical state that's represented by these peaks that is passing through oxygen and carbon that is adventitious. So the rise in the background is related to vanadium passing through a material that does not contain vanadium, and hence we see this rise in the background. But this background may also include background signal due to the chemical state we see in this particular vanadium oxide here, and also the metal. So this vanadium background signal is not unique to this particular vanadium oxide.